Hello, everyone. Today we continue to talk about some structure theorems for Ricci shrinkers. Recall that a Ricci shrinker is a complete Riemannian manifold Mng coupled with a potential function f so that it satisfies an elliptic equation that is Ricci plus cation f is equal to G over 2. Now I can redefine the left-hand side for this equation by a new Ricci curvature, that is the Ricci f. This is so-called the Becquerel-Emery-Ricci tensor. So that means the Ricci shrinker soliton equal. So that means the Ricci shrinking equation can be regarded as the Einstein equation with respect to the Becquerel-Emery-Ricci tensor. Now, first of all, I will talk about the volume comparison theorem. Just like in the Einstein case, we have the volume comparison theorem with respect to the Becquerel-Emery-Ricci tensor. So this is proved by Wei and Wiley. So assume that we have a smooth Riemannian manifold coupled with a potential function f, which satisfies the Ricci f is greater or equal to 0. So this is true in our Ricci shrinker case. And we have a control of the gradient of f, so that the gradient f is bounded by a. Then for any q in M and R greater or equal to S greater than 0, we have the following comparison theorem. That is the BQR VF over BQS VF is less or equal to e to the AR times R over S to the NS. Here, recall that the VF is the weighted measure defined last time. This is e to the negative f times dv. Now, notice that this measure is more natural in the setting of Ricci shrinkers. So with respect to this new measure VF, we have such volume comparison theorem. Now you can compare this to the classic Bishop-Gromov comparison theorem when the function f is equal to 0. So when the function f is equal to 0, here the a is equal to 0. So that is exactly the Bishop-Gromov theorem. Now we will not prove this theorem because this is exactly has the same strategy as the proof in the Bishop-Gromov theorem. You just need to compare the change for the volume form along any radial geodesic, then we can derive this. So I just want to mention some consequence for this level. So first of all, since we have the estimate for the potential function f for the Ricci shrinker, then we can control its gradient on any geodesic form. Now we assume MGF is a Ricci shrinker. Remember that last time we have derived some control for the potential function f, which also controls the gradient of f. That is, we have gradient f squared is less or equal to f. Now, if we only restrict ourselves on a region so that this region is defined by f is less or equal to d, then we can control that number a. So assume, so then we have the following comparison theorem. BQR over BQS is less or equal to C dn, that is a constant, only depends on d and n times r over s to the nth. Here, we require that the BQR is included in the region F is less or equal to D. So the reason is if F is less or equal to D, then the gradient F is less or equal to square root of D. So we can control the absolute value of gradient F. So we can use the comparison theorem by Wei and Wiley to give an estimate for that. Now, another aspect is since the original comparison theorem is with respect to e to the negative f dv, and in this region, when f is less or equal to d, we know that we can have the lower bound and upper bound, so that e to the negative f can be compared to each other as long as we restrict it on this region. So in particular, when s goes to 0, a special case for this is when s goes to 0, we have an upper bound estimate for BQR, which is C dn times r to the n. So that means as long as BQR is controlled, is included in the region f is less or equal to d, then we can give an estimate for its upper bound. Now, a special case is when q is equal to the minimal point. So let's see a special case is if q is equal to p, which is a minimal point. We have an estimate for that, that is BPR is always bounded above by C depends on D, N, and R. Notice that this estimate is not very precise, that it doesn't give us the increasing rate when R goes to positive infinity. So we will try to derive a more precise estimate. Now, we prove the first theorem in today's lecture. This was done by Chow, Zhou, Haushofer, and Muller. So they show that if MNGF is a Ricci shrinker, then there exists a constant C which depends only on the dimension such that the BPR is bounded above by C times R to the nth. So here, the P as before is a minimal point of F. Now, before we prove this, one can compare this with the volume comparisons by Wei and Wiley. You can see that if we directly use the comparison theorem, we can only give a rough bound as we obtained before. But this bound is not very precise. It might be worse when R goes to positive infinity. But for the theorem, one, we can give a precise increasing rate. That means the volume for the ball increases at most in the Euclidean way. Okay, now let's prove this theorem. Now the idea to prove this is to use the property for the potential function f. As we have proved last time, the function f is almost equal to the d squared over 4. That is, to estimate the volume for the geodesic ball, we can estimate the volume for the region bounded by the level set of f. That is, we try to use the level set of F to somehow replace the geodesic sphere. So now we can define auxiliary function rho as 2 times square root of F. As we proved last time, this function rho is almost equal to the distance function to the minimal point P. So we will use this rho to replace the distance function. Now, in particular, we can compute the gradient rho as the gradient F over square root of F. So this is always less or equal to 1. So its absolute value is always less or equal to 1. Then, to estimate the volume for a geodesic ball, we can estimate the volume of the region bounded by this rho. So we define VR as the volume for the region when rho is less or equal to 1. Since rho is almost equal to the distance, so VR is comparable to the volume for the geodesic ball with the radius r. We also define another function chi r, that is the integral of the scalar curvature over the region when rho is less or equal to r. So this is with respect to our given volume form. So our goal is to show that VR is bounded above by r to the x. Now to do this, we can compute the evolution equation for VR along the direction of r. So this is the reason why we choose the rho instead of the distance function, because the rho has the better regularity. It helps us to do the computation. Now we derive the following identity. So first of all, we notice that NVR minus 2 chi r is just equal to the integral on the region rho is less or equal to r, n minus 2r. So this is simply definition. Now by the identity of Ricci-Schwinker, this is equal to 2 times the Laplacian f. So this is the identity we derived last time. Now we can use the integration by parts so that the last integral is equal to 2 times the integral on the boundary of the gradient of f. So notice that this term is always non-negative, so we can derive some weak inequality, that is NVR is always greater or equal to 2 chi r. Or in other words, the chi r is less or equal to n over 2 VR. That means the average value for the scalar curvature is bounded above by n over 2. So this is one byproduct in this identity. Now we can compute the last term. First of all, we rewrite it as gradient f squared over gradient f. Then by using the identity, this is 2 of the integral f minus r over gradient f. Now I can split this into 2 parts. That is 2 integral when rho is equal to r, f minus gradient f minus 2 integral when rho is equal to r, r minus gradient f. Now we can use the co-area formula to compute the derivative for VR and chi r. So by the co-area formula, we have V prime r is the integral when rho is equal to r, 1 over gradient rho. Now by the definition of rho, this is just the r over 2 integral when rho is equal to r, 1 over gradient f. Now, similarly, we can compute the derivative for chi r. This is r over 2 integral when rho is equal to r over gradient f. So that means by the identity, the last two terms can be expressed as the derivative for VR and chi r. So we obtained the following identity, that is NVR minus 2 chi r is equal to r times v prime r minus 4r inverse times chi prime r. Okay. So here, since we restrict to the boundary integral, when rho is equal to r, so f is equal to r squared over 4. Okay. Now, by moving around some terms, this is r to the negative nth VR. Its derivative is 4r to the negative n minus 2 chi prime minus 2r negative 1 negative n times chi. Now we can integrate both sides to obtain for any r and r1, we have r to the negative nth VR minus r1 negative n VR1. This is greater or equal. This is equal to 4. That is, we integrate right-hand side. Then we need to use the integration by parts. There's 4r negative n minus 2 chi r minus 4r1 negative n minus 2 chi r1. Then I plus the last integral term, 2 times the integral r1 to r s minus n minus 3 chi s 2 n plus 2 minus s squared ds. So here for the last term, I need to use the integration by parts and combine some terms. Anyway, we know that for this last identity, we always know that this term is non-negative because the scalar curvature is non-negative. And for the last integral, as long as r1 whose squared is greater or equal to 2 times n plus 2, this is always negative. So we choose r1 to be square root of 2n plus 2, so that the last integral is always negative. So by combining all those estimates, we obtain r to the negative n VR minus r1 negative 1 VR1 is always greater or equal to, it's always less or equal to 4r to the negative n minus 2 chi r. Right? Now, by our byproduct in this proof, that is before we derived chi r is less or equal to n over 2 VR. So the last term is actually 2n r to the minus n minus 2 VR. Notice that r is greater or equal to r1. You can see the last term should be much smaller than the first term. So we can actually absorb those two together. We get r to the negative 2n VR is less or equal to some constant c, which depends only on r, r1 negative n VR1. Notice that v, since r1 is a fixed number, which depends only on n, so the last term depends or can be estimated above by c. So here we have used the volume comparison theorem of weight and value. So that is this term. That is when r depends only on n, so the d only depends on n. Okay. So in this way, we can prove that the VR is bounded by a constant c times r to the nth. Since VR is comparable to the volume for the geodesic ball with the radius r, we obtain our original conclusion. Let's see one more time. Okay, now with those estimates, we can show that first of all, the potential function f has a definite behavior. It's almost equal to d squared over 4. Second of all, the volume up, we have a volume upper bound for the geodesic ball centered at P. So it grows at most in the Euclidean sense. Okay, now with all those preparations, then we can go back to the classification theorem for low-dimensional Ricci shrinkers. Classification. Now, first of all, we consider when the dimension is equal to 2. Now, we try to show that any Ricci shrinker is equal to S2, RP2, or the Euclidean space. Notice that we can assume that the scalar curvature is positive by our rigidity theorem. We can assume that if scalar curvature is positive, we try to prove that its universal cover must be isometric to the standard sphere. Then the proof is complete. So for the classification, we first assume scalar curvature is positive everywhere, and M is simply connected. Then we show that it must be the standard sphere. Now, the proof consists of 2 steps. The first step is we try to, first of all, show the manifold itself must be compact. Notice that in the definition of Ricci shrinker, it might be non-compact and very complicated. Now, to prove this, we use the identity we proved last time. That is the Ricci on the gradient f is equal to gradient r over 2. Now, since the dimension is equal to 2, the Ricci curvature is r over 2g. So this identity is equivalent to r over 2 gradient f is equal to gradient r over 2. So in other words, this means the gradient log r is equal to gradient f. Okay? That means the log r is equal to f plus some constant c0, or r is equal to e to the f times a constant e to the c0. Notice that we proved last time that when f goes to, when for any point goes to positive infinity, the value at which goes to positive infinity. So let's say, since the r plus gradient f squared is equal to f, once more we use the identity. We have the scalar curvature, which is equal to e to the c0 times e to the f, should be bounded above by f. However, this is not possible if the manifold is non-compact, because if you choose a point approach positive infinity, the f goes to positive infinity, and that will violate the last inequality. So that implies M is compact. Okay. Now, after we show M is compact, we just need to show that M has constant curvature. Then it must be isometric to the standard sphere. So for the step 2, we try to prove that R is constant. So actually, by our normalization, we can prove that R is identically 1. Okay. Now, how to prove this? We should use a famous identity, which is called the Carsten-Warner identity. So recall this identity, Carsten-Warner identity. So that is if we have a standard sphere, GS. Sorry, that means if I have a metric which is conformal to the standard sphere, and the X is a conformal Killing field, then by integration, the scalar curvature times the divergence X is equal to 0. So here our assumption is the Riemannian manifold is conformal to the standard sphere, and X is a conformal Killing field. Now both conditions are satisfied for our Ricci-Schwinker case, because now we recall we have shown that it must be compact as simply connected, so it must be conformal to the standard sphere. Moreover, from the Ricci-Schwinker equation, we have the 2 times Hf is equal to G minus G minus 2 times Ricci curvature. Now, for 2-dimensional case, the Ricci curvature is just the R over 2 times G. So this is 1 minus R times G. In other words, the Lie derivative of gradient F on G is equal to 1 minus R times G. In particular, gradient F is a conformally Killing field. Now we can choose our X in the assumption of Carsten-Warner identity to be our gradient F. Then we can show that the integral on the sphere for R times divergence gradient F must be equal to 0. Now the divergence gradient F is equal to just Laplacian F. Now by the identity of Ricci-Schwinker, the Laplacian F is just 1 minus R. Now I claim that the last integral is the integral of the last inequality is equal to the negative R minus 1 squared. The reason for this is from the inequality Laplacian F plus R is equal to 1. By integration, we have the integral of R is the integral of 1 minus Laplacian F, so it's equal to the integral of 1. That means the average value for the scalar curvature is equal to 1. So by using this fact, we know that the last 2 terms are actually equal to each other. So from the last identity, we conclude that the scalar curvature is identically 1. That means our Riemann surface is isometric to the standard sphere. So not only they're conformal to the standard sphere, they are exactly the standard sphere. So any of that quotient should be RP2. Okay. Now, in this way, we have completed the classification of two-dimensional Ricci shrinker. Now we continue to talk about the three-dimensional case. This is when the dimension is equal to 3. Now I present a proof by Laney and Wallish. Now, what is the advantage for three-dimensional case? The one advantage is the Ricci curvature has completely determined all other curvatures. By this, I mean, in dimension 3, the Riemannian curvature can be written as the Ricci times G minus R over 4 G times G. Here, this product is Kucani-Nomizu product. So that is only holds for the Ricci curvature, since there's no wire term. By using this, we can rewrite the elliptic equation for the Ricci curvature. Recall that last time we have derived the following identity. Laplacian F Ricci is Rij minus 2 Rikjl times Rkl. Now, in the three-dimensional case, we can rewrite the Riemannian curvature in terms of the Ricci curvature. That is this term. I denoted by Kij. In the three-dimensional case, can be written in the following way. That is 2 Ricci squared minus R squared Gij plus 3R Rij minus 4 Ril Rjl. So that means we can rewrite everything in terms of the Ricci curvature. Now one can compute the equation for the Ricci squared over R squared. So the idea to classify the three-dimensional Ricci shrinker is to compute Laplacian F Ricci squared over R squared. Notice that the similar quantity has already been computed by Hamilton in the early 80s when he considered the three-dimensional Ricci flows. Now, by a long calculation and some manipulation of terms, one can compute that this is equal to 2R to the 4th. There are a lot of terms. R times gradient Ricci minus gradient R times Ricci squared minus 2 over R gradient Ricci squared R squared times gradient R, and plus a term P over R cubed, where P can be written explicitly as 1/2 of lambda 1, lambda 2 minus lambda 3 squared times lambda 1, lambda 2 squared plus lambda 2 plus lambda 3 minus lambda 1 squared times lambda 2 minus lambda 3 squared, then plus lambda 3 plus lambda 1 minus lambda 2 squared times lambda 1 minus lambda 3 squared. Now, notice that the P is always non-negative. Here, the lambda 1, lambda 2, lambda 3 are all eigenvalues of the Ricci curvatures. Notice that by the definition, P is always non-negative. Moreover, P is equal to 0 if and only if, first case, all 3 eigenvalues are the same, or lambda 1 is equal to lambda 2 and the lambda 3 is equal to 0. So recall that we assume that the scalar curvature is positive, that is lambda 1 plus lambda 2 plus lambda 3 is positive. So the other case is lambda 1 is equal to lambda 2 and lambda 3 is equal to 0. Okay. So now we can use the identity, which I denoted by star, and we use the integration by parts. Now I multiply the identity by Ricci squared. So now we multiply star by Ricci squared and use the integration by parts. And by integration, we have the left-hand side for this identity is equal to negative integral gradient Ricci squared r squared and gradient Ricci squared. Notice that now we integrate with respect to the weighted measure, because that is the right measure, so that the Laplacian f is self-adjoint. So this is our left-hand side. And for the right-hand side, we have a long term. So I'll just copy that. A long term times Ricci squared minus 2 Ricci squared over r gradient Ricci squared over r squared times gradient r, and plus p over r cubed Ricci squared dvf. Now we can actually combine those two terms, because the left-hand side is equal to right-hand side. If I combine by moving the left-hand side to the right-hand side, we obtained 0 is equal to the integral of gradient Ricci squared over r squared r squared plus 2 Ricci squared over r force r gradient Ricci minus gradient r Ricci, then plus p over r cubed Ricci squared dvf. Notice that here the first term comes from a calculation by combining two terms, the second term on the right-hand side with the left-hand side. So here it involves some calculations. Anyway, so this inequality holds, so this identity holds, means all three terms on the right-hand side must be non-negative. So that implies, first of all, Ricci squared over r squared is constant. Second of all, r gradient Ricci minus or is equal to gradient r Ricci. The third is the term p must be identically 0. Okay. So notice that since p is identically 0, there are two possibilities. The first one, 3a, means all lambda 1, lambda 2, lambda 3 are the same. So I use lambda to denote this. The other possibility is lambda 1 is equal to lambda 2 and the lambda 3 is equal to 0. Okay. Okay, now we can finish our classification. So the first case is 3A. That is when all three eigenvalues are the same. That means the Ricci curvature must be equal to R over 3 times G. Now, by taking the divergence and use the identity, we can show that the scalar curvature is a constant. That means this is a positive Einstein manifold. So we can easily show that the universal cover for our Ricci shrinker must be the space form. That means the universal cover is a quotient. So our Ricci shrinker is a quotient of the standard sphere. Now the other case is when two eigenvalues are the same and the third one vanishes. So now we have to investigate the second condition. That is R times gradient Ricci is greater than R times Ricci. So if we define a symmetric two-form eta as the Ricci over R, then the second condition is equivalent to say the gradient eta is equal to 0. That means this symmetric two-form eta is parallel. Notice that the eigenvalues for Ricci are actually comparable to the eigenvalue for eta. So now we define E to be a unit vector field such that eta E is equal to 0. That is, E is the eigenvector for eta. Since eta is parallel, we can show that. So one can prove that E is parallel as well. Okay. Now that means the universal cover for M must be splitting. So the universal cover for our original Ricci shrinker must be the splitting R times another two-dimensional manifold. So G times G. Since the universal cover is also a Ricci shrinker, so the N square must be, so this other piece N must be a two-dimensional Ricci shrinker. So by the classification and our assumption that the other two eigenvalues are the same, we can show that N squared Gn is exactly the two sphere. Okay. That, in other words, means our original Ricci shrinker, whose universal cover must be isometric to the cylinder R times S2 with the standard metric. So in this way, we have completed the classification for three-dimensional Ricci shrinkers. We have shown that for any such Ricci shrinker, its universal cover must be either isometric to the standard sphere S3 or the standard cylinder S2 times R or the Euclidean space. Now I want to mention some generalization for this result. Now, one reason we can complete the classification for three-dimensional Ricci shrinker is, in some sense, the Ricci shrinker has some non-negativity of the Riemannian curvature operator. Actually, by the classic Hamilton Ivy pinch, we can show that for 3D Ricci shrinker, the Riemannian curvature operator must be non-negative. So this is a classical result. That means automatically those three-dimensional Ricci shrinkers has non-negative curvature operators. But for higher dimensional Ricci shrinker, we do not have such estimate. But if we additionally assume such assumption, then we can have a similar classification. Okay. Now assume a general dimensional Ricci shrinker has non-negative curvature operator, then the MG is a symmetric space. So this result was proved by Montiano and Jopin-Wang. So that means in higher dimensional Ricci shrinker, if we in the first place assume that curvature operator is non-negative, then we can show that it must be a symmetric space. That means that is, it's a quotient of n times Rk, where Rn is a simply connected compact symmetric space. Now one can also slightly weaken the condition. So we can impose the condition like weakly PIC2, even weakly PIC1, which are weaker conditions than the non-negativity of the Riemannian curvature operator. All of those assumptions led to the same conclusion. That is, the Ricci shrinker is a symmetric space. Notice that this result is very important when we investigate the general Asian solution with non-negative curvature operator. That is, we can use this property of the Ricci shrinker to approximate the given Asian solution. So this has been done by many researchers. Okay, now we have finished today's lecture. Next time I will talk about the pair mass entropy and other fundamental estimates.